and there's an uncontrolled fusion reaction.
For 1 gram of fissionable material, you can get...
How far are we from nuclear fusion? Now they're depending on Russia. If they didn't do that, there would be no war in Ukraine. So what can you do now to avoid a disaster like that?
The disaster in Chernobyl was like all around. Earthquake and the tsunamis essentially cut the power to the reactors. Disasters, Fukushima and Chernobyl. When a neutron hits the nuclear fuel, the reactor cannot work as well.
Why did Chernobyl happen? Is it pretty safe, would you say? Hello and welcome back to 3D Media Life Podcast. I'm your host, Dimitri, and today I have a special guest. His name is Oran Lori. He has a PhD in chemistry. He's a researcher in UCI, and he's working on nuclear fuels. And there's a lot of interesting things that are happening in that field, and I'd love to just chat.
Yeah.
Welcome to the show.
Happy to be here. My pleasure.
Yeah, so tell me, how did you get into, first of all, nuclear chemistry?
Well, the road was a kind of a bumpy road. It was like straightforward. I did my undergrad in chemistry, worked a few years in the industry, and then started grad school in a bit different field. It was like more renewable energy and electrochemical devices for automotives, industries, and power grids. After I finished, my advisor at the time met with my current advisor. They had some connection through third party, and she was looking for a postdoc that had some knowledge in material science, ceramic materials, etc. And then that's how the hookup, or the connection was made, and I kind of transitioned from material science and electrochemistry to material science and nuclear fuels. That's how I transitioned kind of from material science in electrochemistry and renewable energies to material science in nuclear fuels, which is not that far, but it's kind of a bit of a transition, that I had to make.
What excites you the most in your field?
So I'm the kind of guy that is very excited with the small picture rather than the big picture. So a lot of people, energy is going that way, and we're going to do this kind of energy. But I like the small research, how materials work inside, how things are happening. So I have my expertise is mostly in ceramics, ceramic materials, electronic properties of them, corrosion, stuff like that, and the underlying processes, how things happen, how atoms move in a material, how a ceramic or a material corrodes in time, and
are things like intuitive when you're studying it, or it's not intuitive? On the atomic level,
if you understand it well, it becomes intuitive. Yeah, if you know the background, if you understand the background, some more, some less, of course. Some more intuitive, some less. But when you understand the background, when you know the science, it becomes pretty much clear. Yeah, that makes sense.
Are there things that don't make sense right now when you're learning something, or in this field, the more you look into it, it just seems a little bit random or unexplainable?
When you go to the bigger picture, how not the atoms, but why they act, how they act, or the underlying reasons, then it becomes a bit more perplexing.
Give me an example of that.
Well, I think it kind of starts to be outside of my scope, because all the matter of the quantum physics and how, for example, we have the nuclear of the atom, right? So we know that it's has like a positive charge and all that, but how does that positive charge manifest, or how does the essential particles get it to be positive charge? This is becoming more and more, for example,
like theoretical.
Theoretical and not really understood. Or, for example, we know how bonds are made in chemistry and stuff like that, but when you get to the quantum, realm, it becomes very, very unclear. For example, how can a particle be in two different states at once, and it's all a matter of how you look at it. If you test it, then in one state, but if you don't test it, it's a different state. So it's becoming more and more, when you go to those realms, those fields, it becomes more and more perplexing. How can that be? What are we missing here?
Do you ever go in those fields? Does it involve your day-to-day work?
And not so much. Sometimes when I need to, or when I'm working with others, but it's not so much in my scope.
So what do you do when you run into something that's perplexing and unexplainable, or?
Well, first of all, we try to look at it in different angles, try different maybe methods to try to understand it. That's what we usually do. Not always we get the result or the answer we're looking for. So, well, at the end of the day, our job is like to publish papers. I hate to say it, but that's the truth. So if something is not up to our understanding or is unanswerable, we just kind of like
move along.
That's how it works.
Like you're right now, the practical application of what you're doing is trying to discover alternative fuels, or better, improve the nuclear fuels.
Currently, what we're trying to do is understand why nuclear fuel will fail under nuclear reactor operations. What are the mechanisms that it fails, and how we can get the current nuclear fuel to be better in overcoming those mechanisms. So we mostly, the most common nuclear fuel today is what we call uranium oxide, UO2. And it's just like a very solid, typically in the form of pellet. That's the most common. And while the reactor is operating, there are many fail mechanisms that happen that eventually will degrade the fuel and make it unusable. So that's our main goal: understanding those mechanisms, those processes, why they happen, how to mitigate them, maybe get some insights, so like the underlying science or chemistry or of those like processes. Yeah.
What's the state of the fuel now? Is it pretty safe, would you say? The most modern.
You mean the fuel itself, or
yes,
how the reactor is engineered?
Let's say both. Let's say both.
So, well, it's a nuclear fuel. If you leave it outside, it's not safe for anybody. Well, not really the one we use, because we use more controlled fuel. I'm sure you've heard of enrichment.
Yeah.
So in reactors, they use enriched fuel, and we use the unenriched, depleted fuel, because it's just for research purposes. There's no reason to put us in risk when we work on that. So
and there's no risk whatsoever in your line of work?
There's always some risk, but there's so many fail-safes and so many barriers that we use that it's highly unlikely.
Do you test for radiation?
Yeah, always. Like whenever we do radioactive work, there are a bunch of monitors that is operating while we're doing the work. So if something happens, that is being detected within a second. And then after we're done, we have to frisk ourselves to see if we have like residuals and stuff like that. So
have you ever had an incident where?
It's not really an incident. Sometimes you can get artifacts. I was in Los Alamos for a few months, and it was raining. So sometimes when water gets stuck to your feet, some residuals from the lab can stick to it, and then when you want to go outside, you freeze yourself, and that the whole parameter is up the charts. So wow. That's something but it was like a minor incident, so like something, but it's very well controlled and handled.
Has it always been well controlled, or like 30 years ago it was 40? Like people used to get cancers and stuff.
Yeah.
Do you think now it's like relatively safe? You don't fear that you might,
No.
God forbid, get cancer or something?
It's been pretty safe for the past few decades. All those incidents that are known or people heard of are fairly in the distant past, mostly after maybe the 40s, 50s, 60s, when they have very lax rules and regulations. I don't know if anybody know that movie about like a fat child, or the name. This movie shows the way they had done the experiments on what they call devil's ball, something, which is pure plutonium, and you can see in the movie that they were very, very lax and very, everything was okay, and they had very little barriers to protect themselves. And
So what happened to them?
At some point it just like went out of control, and one of them got exposed to a lethal dose and he died.
Oh wow!
There was I think the
Those in the
late
States?
40s. Yeah. It was I think Los Alamos, if I'm not mistaken. Was either late 40s or early 50s. I'm spacing on the name of the guy, but he's well known. The one of two guys that actually died from exposure.
I'm sure in Russia that probably happened all
Yeah,
the time.
oh.
Soviet Union, but
Yeah.
nobody knew why.
Nobody knew
He
why.
just didn't come back from work today.
The result was Chernobyl. Yeah, I know.
Yeah.
That's true. But a lot of other people got sick. Yeah.
Speaking of Chernobyl, why did Chernobyl happen?
So Chernobyl happened due to a number of reasons. Not for it was the reactor was not planned well to begin with. A lot of people did not follow regulations, so
Do
it
we
was
still have the same reactors out operating?
no.
They're all
The reactors are different. At least the part that was very crucial from like at this point, will it go further or just stop? And at some point, crucial point, they had to do something, and that component they had to pull in the reactor did not fit or was not planned well, and that just got the reaction to get out of control. It's not planned. It's not designed that way today, and for a while. So it was bunch of reasons, accumulation of reasons that got a lot worse than it should have been. And
Was it like something that out of negligence could have been prevented, or it's
some
just a
negligence,
natural
yeah.
thing they discovered? They made mistakes, you know?
No. It was a poor design with negligence. Yeah, that was Chernobyl.
So the poor design, was that because of lack of research, or they just didn't care?
That's a good question. If they didn't care, maybe they didn't care in Soviet Union back then. But back then, those components were up to specification. That's the way they used it. They weren't supposed to contain this kind of situation, and when the situation arose, they weren't up to the task. Because under normal circumstances, those components should do this job as no problem. But when you get to that critical point, you cannot use those components. And I can get into specifics if you want.
Yeah.
So what happened in Chernobyl was that they was trying to do an experiment in the reactor. And in order to do the experiment, they had to lower the power of the reactor to about 50% of the normal usage. And because of that, when a nuclear reactor works, there's what we call fission products. There's some kind of gases that accumulate in the fuel because of the fission reaction. And if you guys want, I have like a very good
Which slide is it?
image. Just continue, you'll see it, of a fission. A little bit more, yeah. So, yeah. So, if you see here, when you have the uranium and it's bombarded with neutron, it splits into two, and one of the products is just barium, which is solid, but the other one is krypton. It can be krypton. In other cases, it can be xenon. Those are inert gases, and they accumulate in the nuclear fuel. So what happened that when the normal operations, at some point they just cleared out at some point, because the reaction goes on, and when it's high power, the neutrons and whatever you have inside just clear out the krypton, and that's not a problem. But they were working on 50% or even less than 50% of the, and that on one hand led to the accumulation of the xenon in that case, and not clearing it out because it's not enough power. And what that happens, what that leads to is over time, the reactor cannot work as well. So the power kind of diminishes. So they got to about 7% at some point, but they decided to do the experiment they were planning anyways. And 7% is not enough power to do the experiment. So they decided to remove all the fail-safes and all the control components.
So that's pure negligence of the whole thing.
Yeah, in order to make the experiment work. And at some point, there were no fail-safes, no control components, and the reactor operation just got out of control, got overheated.
So why did it get overheated? It wasn't strong enough to handle or something? Because
I have another slide if you guys want, but the way to control the reaction is to pull in and out control rods. Those control rods have a very high cross section of absorbing those neutrons that get the reaction started, right? So when they're pulled in, the reaction basically stops. So you can pull them in and out, and they control the height of them inside the reactor and out in order for the reaction to be slower or faster. So if you want to shut down the reactor totally, you have to pull them all the way in, and the reactor shuts down. But what they did, they pulled them all the way out. They just removed them from the reactor. So at some point, it became uncontrollable. And it overheated as a result. And this is where the poor design comes into play. Those rods, which are mostly made of boron, it's a very high. It has the highest ability to absorb neutrons that make the reaction happen. Those boron rods were coated with graphite. So maybe I should talk about how a reactor is built before. So if you go further, you'll see another. Okay, that's good. So this is the right picture is a nuclear reactor. And you can see on the left side of the picture those rods, black rods, inside a container which contains water. So you have the rods, which are the nuclear fuel, basically. The red rods, the nuclear fuel, they go through the nuclear reaction. Those black rods, the thin black rods, are the moderators. The control rods. They are made of boron. Usually they are meant to stop or moderate or control the reaction. And the water is called the moderator. So the thing is, when a neutron hits the nuclear fuel, the nuclear fuel splits into two, but in this process, it also produces more neutrons. Those neutrons are very, very, very fast. They're called fast neutrons, and fast neutrons have a hard time to make the chain reaction that is needed in the reactor, because it's just one-time thing. They become fast, they just go, they escape, end the story. No chain reaction, which is needed in the reactor if you want to get sustainable or sustained power manufacturing. So here comes into play the water. They're called moderator. The role of the water is to get the neutrons, the fast neutrons, to hit them, and then slow down and become thermal neutrons. So a thermal neutron can hit another uranium atom and then get the whole thing going again. So it's kind of
balancing out things.
Exactly, balancing out. You have the water that's supposed to get the chain reaction going, and you have the control rods which supposed to get it slower. So that's how you control the rate of reaction, and then also how you control the power that you can extract from that reactor.
Once you start the reaction, it pretty much goes on until the fuel's exhausted, or you can stop it?
You can stop it if you use the control rods all the way down. So they just stop the neutrons from bouncing from atom to atom, and they just absorb the whole thing. That's it.
So essentially, that reaction of having the neutrons flying around there, that creates a lot of energy and heat.
Exactly. So also, the reaction itself creates a lot of energy. And then the heating of the neutrons with the water, also more energy. So that can get, if you don't control it, that can get to 5,000 C easily, or 8,000 Fahrenheit easily. That temperature.
What's a good reference point? What's 8,000 Celsius? How hot is the sun?
The sun's surface is about 10,000 degrees Celsius. The inner parts are about million. Most important point is that it gets to a temperature that can melt the nuclear fuel. When that's melted, that's called a meltdown. And this is like a nuclear fuel most problematic failure, which can get pressure up and explosions and all that. So this happened in both of those disasters, Fukushima and Chernobyl.
Why did Fukushima happen?
So let's just close it up with the Chernobyl. So the water sometimes is replaced with graphite. So graphite is also a moderator. It slows down the neutrons. In addition to water, or completely? No, it depends on the reactor. Sometimes they use water, especially heavy water, to those who know what it is. Sometimes graphite. It's just like. So in Chernobyl, they only had graphite. So Chernobyl they had water, but the control rods, the Bohr control rods, were coated with graphite. So what happened was that at that point, putting graphite in there just made the reaction even worse. So that's a poor design that they didn't figure out because they didn't think that would happen. So at that point, when it was already critical to put the control rod back in to get the reactor to stop, the reaction to stop, but instead it just made it worse. And at that point, the pressure was skyrocketed, and there was explosion that detached the cap, the dome of the reactor, and then just. Did you watch the show Chernobyl? I did. It was an amazing show. An amazing show. How accurate is it? It's pretty accurate. They tried to do it pretty well. They didn't go too much into the specifics of how that works, but it's a pretty good show for laymen, I guess. Yeah. Yeah. It was a pretty good show. You asked about Fukushima. So Fukushima was not so much about lacks of regulation. It was just try to stay closer to the microphone. So it wasn't so much about not following regulations and poor design, because they had it contained at some point with minimal collateral damage, so to speak, and the damage was mainly from the earthquake and the tsunami that followed it, rather than actually from the disaster. But what happened there, that the earthquake and the tsunamis essentially cut the power to the reactors.
Wouldn't they have thought that through, that that's a possibility?
They did. They had like emergency generators, but this whole thing was so massive that a lot of like equipment just went under, and that includes the generator. And even so, even when you shut down a reactor, sometimes it still gives like 50% of the power. And if you don't control that, over time it will heat up and overheat and get through all those horrible steps that I just mentioned. So that's kind of what happened in Fukushima. But
so what's the issue of losing power again? If you lose power in the reactor...
So the reactor is always heats up. It always... in a process, either the water collision, either the actual reaction, so it gets to very, very high temperatures, and which is supposed to. That's the way it is. That's how you convert the heat from the reactor with water and get the steam and all the stuff that makes the electricity. You need that to happen, but not when it's breached. So what happened in Fukushima, that they didn't have a way to cool down the reactor. So the reactor heated up, and got to that critical point when the fuel melt, and that was the meltdown.
And how do they cool the reactor? With the rods also, or no?
So that's one way to like not actively cool, but like passively cool. When you just stop the reaction.
So why couldn't they stop it?
The reaction?
Yeah, with the rods.
As I said,
Fukushima.
As I said, they stopped it. But even when you stop
it still goes like 50%
you have like
power.
10 to 50% operation, which should be contained by the cooling system.
And the cooling system is run with the water, or?
The cooling system is the water, and they have like pipes all around the reactor core, which also, I think they have also water and heat converters to do conversion of heat and take heat out of the reactor.
So that needs electricity.
Exactly. And
if the reactor is still producing power, why can't they use that?
That's not how it's built. Maybe like in retrospect they can like rewire it to do that, but that's not how the reactor is built.
It seems ironic. The reactor is producing a lot of electricity, and yet it fails because there is no electricity.
Yeah,
it's feeding from electricity from another source essentially to operate.
Yeah, and even then, 10% of the reactor would not be sufficient to
run the
to like cool that down and efficiently enough.
And their backup generators also failed.
Yeah, some of them, and so, but they actually, I think they used at some point like seawater and stuff like that to manage that. But they got it contained. It took a while. I think it took about 4 days, but they got it contained at some point and without really serious collateral damage. But that really...
Did it melt like in Chernobyl or no?
Yeah, they both smelled down, but the disaster in Chernobyl was like all around. It just, all the radioactive material, it just got around with the wind, got to Ukraine, like incredible radius. Fukushima, they managed to keep it
contained,
relatively speaking. I don't think that many people died from that contamination. I think most people died from the actual disaster, the earthquake.
So what can you do now to avoid a disaster like that? I mean, natural disasters are bound to happen. Earthquakes, tsunamis, especially like in California, right? We're prone to earthquakes.
Yeah, so California doesn't have too many reactors. They have I think 2 currently working reactors.
But why can't you design it in such a way where it's not there's no opportunity for this disaster to happen?
So That's when the what we call the fourth generation reactors come into manufacturing, or like they try to get them to get some progress in research in them.
What generation was Chernobyl?
I think it was 2.
And then Fukushima?
3. That's for sure. I'm not sure about. I think Chernobyl was 2, but don't quote me on that. But Fukushima was 3. The fourth one, which are not active yet, there aren't any fourth generation reactors yet.
But they're supposed to be substantially safer.
Yeah,
right?
substantially safe. Mainly because they use molten salt as the moderator rather than water.
And why is molten salt so much better?
So, first of all, it has a very high boiling point. So water is just 100 degrees. So when you go, when the reactor heats up, it becomes like gas, and gas like build up pressure. And even so, if it goes even higher than that, water can split to hydrogen, and then
that's the explosion.
That's explosion. Molten salt doesn't work like that. It has a very high boiling point, so you can get to very high temperature, and it will still remain in the liquid form. That's one. Second of all, the properties of the heat conversion. So it takes heat. The water takes heat from the reactor and convert it or move it to the steam, and like something needs to take the heat from the reactor and use it for the electricity, right? As I mentioned, first of all, it doesn't boil that really like water, and it doesn't produce hydrogen or gas. It has a better way to convert the heat from the reactor, to take the heat from the reactor and like disperse it elsewhere. And that's why so and then when something happened to it, if there's a fail in the molten salt, it just precipitates a solid and not like make
And how come the generation 3 and 2 did not use molten salt? Is it just a new discovery?
Yeah, it's a new, not discovery, it's a new development. Yeah, molten salt has been increasingly researched, not only for reactors, for a lot of other stuff that I've been doing myself over the years, in a lot of like other fields of science, such as extraction oxygen from lunar soil and stuff like that, which is kind of exciting. But it's been researched in the past maybe 20 years.
You know what comes to mind
more.
when you say molten salt? I don't know why. Dead Sea.
The Dead Sea?
Yeah, well, it has just salt water.
Yeah.
Highly salt.
So that's not the same thing.
Not the same.
Not the same thing. So the Dead Sea is just water with a lot of ions or salts dissolved in it. So it's like very salty water.
A molten salt, you literally take salt and melt it?
Yeah. Molten salt is like taking the salt in your house that you use to spice up your cooking and just melt it.
Wow.
Yeah, so
At what temperature does it melt?
So it depends on the salt. Some salts, I think the one in your house is maybe a few hundred degrees Celsius. I'm sorry if you guys want me to talk in Fahrenheit.
Okay.
I just have to convert it. That's the one in your house. Some of them are very high temperature, like 1,000, 1,500.
Which one do you normally use for a generation 4 reactor?
I'm not sure exactly. I think it's kind of something carbonate or something. I'm not sure, but some of them.
So have you tested it already?
No. We're not researching the engineering of the reactor. There's some places, mostly national labs, they work on how to engineer those places, the new reactors, but it's not operational yet. I'm not even sure that they had like a prototype. It's just like a technology that they know will work, and they need to actually assemble it into a reactor, but they haven't done it yet.
Okay, quick break from what we're talking. I just want to go back to the Dead Sea. Ask your opinion.
Yeah.
From the biblical account of what happened in that area with Sodom and Gomorrah,
Mm-hmm.
why would there be so much salt? What could have happened?
You mean scientifically speaking?
Yeah. Let's say there is some kind of God used some natural means to wipe out that area. Why would there be so much byproduct of salt in the water? Seems like it's almost like a crater now. That's filled with it's the only body of water that has so much salt, correct? Or there's other ones
Well,
in nature?
everybody water have some salt in it.
No, but
It's just
to that amount.
That amount, I think it's the highest amount that I know.
Do you think it's a coincidence that it happens to be in that exact area where we have biblical account of some catastrophe happening, some kind of a reaction?
That could be an explanation.
Is there any kind of chemical reaction that would produce that byproduct?
The salt? It's more like, well, the way that as science understand that the way that the Dead Sea was formed just made them very susceptible to precipitation of salts. And because it's like a dead end, doesn't go anywhere from the Dead Sea, so it's kind of like a lot of like salts that just stay in there.
But there's no like some kind of event that could have happened that would explain it.
You mean like the biblical description?
Yeah.
Could be. If
What does it say in the Bible that what happened with Sodom and Gomorrah?
That God did some kind of miracle, which I'm not sure I can translate into English, but he used sulfur and used a lot of like materials to destroy Sodom and Gomorrah. And even Lot's wife became a
Statue of salt.
statue of salt.
Can that be explained scientifically in any way, shape, or form?
The event?
Yeah, the event. We often know that God uses natural means, like if
and the very good example, which I very like, is the Exodus.
Yeah,
I don't know if people saw that movie, which I like. I like most of the explanations.
We're pretty cool.
Yeah, pretty cool. They tied it to a known disaster, which is kind of cool.
So what about
if we know about of a known disaster in that era? I'm not familiar with, but you cannot rule that out. It could be some kind of a volcano erupting, which has sulfur and has all like the basic material in a volcano is just rocks or salts. So maybe a volcano erupted, and then a whole this thing happened, and some of the residual materials from the volcano just settled over there, and then that's what you see now as the rocks and salt, overabundance of them being in that area.
Okay.
I'm just not sure that maybe if you go back enough, you'll find some evidence for a volcano being there, but that could explain that event in some way, I guess.
Okay, let's go back to the nuclear reaction.
That's just like I know, just the top of my head. I haven't thought it through enough. Okay, so where were you?
So we just finished talking about Fukushima.
Okay, so
and now the ways the Generation 4 reactors are designed, they're going to use molten salt.
Yeah.
What about? I think we talked off camera before. You were saying like how some of the fuel that you're using is you're just making it larger to make it safer.
Yeah. So the fuels that are used today have some basic or essential like failure mechanism that they go through, and that's like the nature of the material. So maybe you go to one of the slides and I can
Which
explain. The one with the microscopy, maybe go more, no, the other way. More, a bit more, yeah. Okay, so those are like electron microscopies of not specifically a.
Those are nanometers?
Yeah, so the right one is a nanometer scale image of skin electron microscopy. The left one is micrometer scale. Those are not specifically fuels, but those are what we call surrogates. Because sometimes it's hard to research actual fuel because it's kind of dangerous. So we work on surrogates. Materials that resemble fuels in a lot of like properties, and we can use them to like
What's an
understand.
example of a surrogate?
Cerium oxide, for example.
It's very similar to uranium.
Yeah, it's similar to uranium in terms of the uranium oxide, in terms of the structure, crystal structure, and bunch of other density stuff like that. So we use it as a surrogate material to research the general mechanisms or processes that go through. So, so specifically today, the nuclear fuel is just pellet of uranium oxide that's pressed using a mechanical press, and the goal. So I think I mentioned it, that the one of the problems with today's nuclear fuel that it accumulates gases in there. I think I mentioned that when the split, and one of them is a gas, one of them. So those gases just accumulate in the fuel, and they create or they form all kinds of failures in the material, like cracks. They can form all kinds of like creep,
so
stress.
The finer the fuel, the more it can accumulate, essentially, right?
So this is just a slide showing how you get from nano to micro. So see, but essentially they're mostly micro meter scale, just not as big as those. There will be maybe 1 micron, 2 micron particles, and in that sense, it's harder to retain those gases inside because those grains, we call them grains, are so small. If you get the grains to be larger, you can retain those gases inside, and then they won't form those fails.
So you want to retain the gas inside.
Yeah, we want to retain the gases inside and not let them do make effects like cracks and all kinds of like mechanical.
So essentially,
processes.
the fuel becomes more stable in that sense.
That's exactly, and can operate for a longer time.
Do we already have newer fuel like that's ready to be used?
So yeah, I'm not sure that they use it in all the reactors, but some reactors started to use that fuel. So the way with it we do it, how do we actually make those grains larger? We put some very low content of contaminations in there. So it's not UO2, uranium oxide pure, it's uranium oxide with a very low amount of other atoms, such as chromium, titanium, and very low amounts. I'm talking about maybe not more than 1% of the fuel. And when you introduce those contaminants in the synthesis part, you get the grains to be bigger. So here you see about like maybe 30 micrometer of grain. You can get them at the right temperature, the right contaminants to be even 100, 200 grain growth.
So that would basically reduce the chances of gas escaping by like 2 or 3 fold.
Exactly. So that's and the for example, for chromium, a dope we call the doping. You dope material with another contamination. So we call it doping. So chromium doped UO2 which is a fuel today, is starting to get into circulation in nuclear reactors
That's
more
very
and more.
cool.
Yeah.
So
that's what
by what amount, like, the risk would be reduced if we're using this along with molten salt and this new fuel? Is it like twice as safer, 3 times safer? Is it hard to estimate?
It's hard to estimate exactly, but I think that the new generations, regardless of the work that we do, in terms of the engineering that they implemented, will overcome any of those last disasters that have happened. No more Fukushima, essentially, no more Chernobyl.
So at that point, there would be absolutely no argument not to go nuclear.
There are other stuff that can happen.
Such as?
At the top of my head, I don't know. Like, I don't have. I don't want to think about it.
But even now, it's already considered the safest source of energy.
It's a very safe source of energy. The thing is, it's hard to convince people that along the way we won't find something else that is problematic, and it probably will happen. You do it, you get the reactor up and running, and then we didn't think of that. This is a sort of a problem, and that's what people are mostly concerned of. We don't want to start recommissioning or commissioning new reactors because we don't know what's going to happen.
When was the last reactor commissioned in the United States?
I think it was 2012, maybe.
No, not too long ago.
Not too long ago, but the peak was 112. I think it was the end of 90s, 98. But ever since then, it's always they got they decommissioned more than they commissioned.
Same in Europe too, right?
Yeah. So
Except
Europe,
France.
Except France, yeah. Europe is France is gonna keep their stuff up and running, but Germany, for example, destroyed almost all the nuclear.
Which is kind of stupid because now they're depending on Russia.
Exactly.
For gas.
So now they're starting again to maybe not decommission everything, and they're rethinking their strategy. But
like, arguably, you can say if they didn't do that, there would be no war in Ukraine.
Probably, yeah.
Like Putin knows how much they're depending on the energy, and he just does what he wants.
I agree.
And he's funded probably the war by selling.
I agree. Totally agree. They did a very crucial mistake off of like one, very, very specific disaster. It's like
the Fukushima.
The
Fukushima. All happened after Fukushima.
Yeah, it's all happened after Fukushima.
And they have no danger of tsunami, no danger of earthquakes.
If you pull inland enough, no, like what could happen? Like, no tsunami is gonna get to like Munich. No, that's not gonna happen. But they're afraid, and out of that fear, they started decommissioned. We had a student in my lab that went back to Germany to start working on decommissioning of reactors.
I think it's almost like politically driven more than anything else.
Probably. People, when people don't know the science, they're afraid.
I mean, we need more energy, like with all the data centers right now sucking up so much energy, with cryptocurrency, with advancement of AI, we need more and more and more energy. Not even talking about electric cars, which is also a big problem.
Yeah. To be honest, like the U.S. is in good shape. They have like 20% of their energy production from nuclear. It's not bad.
20 is still low.
It's still low, but
why not make it 80%? Like, what are the other sources? They're still burning coal?
It's still coal, natural gas are the main ones.
Well, natural gas not bad because we have abundance of it. The coal is polluting the planet.
Yeah, but if you look at like greenhouses, natural gas also. It doesn't contribute. It contributes to greenhouse gases. So if you want to control that, coal is polluting, which natural gas doesn't so much. But if you're talking about the whole picture of climate changes and you want to control that, natural gas is not the solution. It's not. It produces carbon dioxide, and water.
How far are we from nuclear fusion? Is it still the elusive 30 years away or something?
Nuclear fusion, as far as I last heard, they are expecting to have something maybe out of research by 2050. So it's very hard to control. You have to remember, it's like 1,000 to 10,000 times more powerful than fission. So you need a lot more means to control it. I think there was, not long, maybe 6 months ago, a recent company declared that they were able to control it fairly, like in a good way. But that's which was a breakthrough. But
what's the fundamental difference between fusion and fission? Let's go back to this slide right here.
I think I have some more. So, okay.
On this slide?
More. I have like some illustrations. Okay, so you have fission on the left and fusion on the right. So fission,
you're splitting.
You're just splitting. So splitting can happen in two ways. Either the atom decays naturally, which is kind of fission, or you add a neutron to it, and then it becomes stable, and then it's like split. That's how, and usually it creates some more neutrons that can sustain a chain reaction.
So at the core of this, it's all goes back to E equals mc squared. There's so much energy within every atom, right? Within every particle. And so when you break it apart, there's releases energy, and that's the
the release of energy is because the mass of the mother atom is not the same of the daughters. So there's some mass difference, and this mass becomes energy, like we know from Einstein's equation.
And that's how all nuclear bombs work. Essentially, you just split an atom, and all this release of energy because the mass is decreased.
For 1 gram of fissionable material, you can get billion, about 100,000 TNT power.
It's crazy.
It's crazy. And it's like nothing. The fusion...
And sorry, as you're splitting it also the byproduct of that is also radiation.
The byproducts... some byproducts are also decaying naturally, They can decay naturally and be problematic in terms of like radiation,
Okay.
Not every one of them, but some of them.
Uranium especially.
So when uranium is splitting, it's splitting into different things. Barium, as you remember, and krypton. I think the krypton is less problematic, but the barium is still radioactive and can decay. And you always have leftovers. Even if you consumed most of the nuclear fuel, you still have leftovers in there, and they're radioactive. They decay naturally.
That's called the nuclear fuel byproduct or waste.
Waste.
But I heard that now they're developing ways to use the waste as fuel as well. Did you hear about that?
So they're trying to like recycle it.
Right now they're just storing it underground, and there's no real solution. Somewhere in I forgot.
Some desert,
No, not even. There's one place in Europe they're building. I forgot Finland, not Finland. They're building massive.
I know
storage.
what you mean. It's not. I think it's
in the mountains.
It's Switzerland.
Switzerland.
Yeah, Switzerland.
I thought it was more north. One of those countries.
Because I know that they use water from Switzerland to test if those if this nuclear fuel waste goes into the water. So they take the water from Switzerland to test the whole system. So that's why I think it's Switzerland.
I feel like unless we come to using fusion soon, that has to be some sort of a solution, because storing indefinitely nuclear waste is not good.
So that's one of the things that there's been research. How can you store nuclear waste for 1 million years?
But
10 million years.
Where?
There are enough places that far enough from like any population.
I don't know.
And
why not recycle it? Like,
because it's all about the money. Recycling is money consuming, but
it's theoretically possible.
But you will still have waste. Even if you recycle it, you'll still have waste.
There's no way to indefinitely recycle it, or
Not everything. Some of it, yeah. And
how
that's
much? 80%, 50.
So when a nuclear fuel is spent, that means you used it as much as you could. I think it has maybe 20% unused fissionable material, if I remember correctly. So you can recycle that 20%, but all the other 80% is just waste. There's nothing to do with that. It will decay naturally
And what's
and
the
release
half-life?
of those I think it's like decades or something like that.
Oh, not. I thought it was like hundreds of years.
It
hundreds
depends
of
on the
thousands.
product. If it's the uranium residues, it's decades,
Oh, that's
30
it.
years.
It's not bad.
But some of them, I'm not sure exactly, but maybe the barium is like more than that, and it depends because sometimes you split uranium, some plutonium, so uranium has like 2 different types that you can split. So every
How come
product.
in Chernobyl then they say it's like going to be hundreds of thousands of years before it's safe over there? Because the reaction just keeps happening, and it's creating more.
Even if you have half-life of an atom, it doesn't mean that the products doesn't have their own half-lives. It's naturally splits into 2 atoms, but those atoms can be radioactive as well and split themselves.
Oh, it just continue the chain
So
reaction.
yeah, it's not really a chain reaction; it's just natural decaying of atoms. But just because one of them split doesn't mean that the products don't split even more. So it's maybe you got rid of the uranium, but now you have two products that have their own half-lives.
Got it.
So it's not everything is going to like be done with like decades. It depends on the atom on the product. It can be hundreds of years, maybe even more.
Okay, let's go to
Okay.
fusion.
So fusion is just the opposite. You don't split an atom, you just like fuse them together. And there are number of atoms that can do that. I didn't bring here the table, but there's in the periodic table there's like a line that the one side of it, those atoms can go through fusion.
Come closer a little
Oh,
bit.
sorry. So the left side of it, atoms can go through fusion, and the right side of it, they can go through. For the fusion reaction, what happens that typically they use 2 atoms of hydrogen. That's what they called hydrogen bomb, if you remember from back in the day. And they create a helium atom. And this reaction can release 1,000 to 10,000 more energy than the other one.
So why fusing atoms create? I understand why it happens with fission, because you're changing the mass and that releases energy. Here, it's the same thing. You're just changing the mass.
Yeah.
Is the mass becoming smaller?
The overall
from fusion,
mass, yeah.
From fusion.
Yeah.
Got it, okay.
In every nuclear reaction, you have some conversion of mass to energy. The question: how much mass do you have to convert? Here, it's less than. For fusion, it's less than fusion.
Like
For fusion,
1,000 times less or something.
Something like that. Yeah.
So, why is it safer to fuse? Theoretically, they're saying there's no byproduct. Radiation is not going to be a byproduct of fusion, right? Or very minimal.
Very minimal.
Why is that?
First of all, you don't have products. Essentially, the product is helium, which is not reactive. The only thing that is a bit problematic is it releases a neutron, like you see and that can be some kind of ionizing radiation, but that can be controlled pretty easily. For the fission, you have a lot of byproducts. As you can see, you have products that can decay naturally. You have 3 more neutrons. It's a whole mess, which you have to control or get those spent fuels and put them somewhere. In fusion, in terms of like handling the spent fuel.
Just have one neutron flying around.
Yeah, exactly. The problem is not so much with the products. The problem is how to moderate the huge amount of power.
Why is it so much more power from fusion?
Because this fusion reaction, the mass difference between the to get to the products, you have some mass difference, right? So this mass is very huge in comparison to fission. You have a lot of mass difference. Mass is being converted.
And the more mass, the more energy.
Exactly. Yeah.
What's the comparison, and how much mass is being lost from fusing helium? You fuse helium with tritium?
No, it's two isotopes of hydrogen called deuterium.
Okay.
Which is the essential component of heavy water, and the other is tritium. And they fuse together to get one helium, and then you
So how much mass is lost when you do that?
Per atom?
Yeah. In comparison to fission. Do you remember the numbers?
You mean like you want like values?
Yeah, just an actual mass lost. So I get some sort of an idea.
It's 1,000 more.
Just
that's for sure.
That's
I'm not. I don't remember the from the top. I have to calculate it.
Have they ever tried making a bomb?
It will be very small per atom. That's for sure. It's very, very small. You're talking about 1 gram.
Yeah.
So 1 gram is like 6 to the 10 to the 22, like 6 trillion atoms. So you get the whole effect of the whole lot of atoms. Per atom, it would be very, very small. You won't even feel it.
How come they haven't tried doing a bomb from fusing atoms? What's the issue?
Hydrogen bomb.
Oh, that's fusion.
The bomb
fusion.
is, I'm not sure. I think they tested it. Maybe France tested it. They tested the bomb, that's for sure. They did not use it on the population yet. Thank God.
The Tsar bomb, I thought that was fission, or that's fusion.
The bomb on Hiroshima?
No, the Tsar bomb, the one the Russians made, the biggest one ever.
Yeah,
that's a hydrogen bomb.
I think so. Yeah, that's fusion. Yeah. I think that the Manhattan Project, they tried to work on a fusion bomb, but it never got to like actual realization.
So that's the whole essence of a hydrogen bomb, is that it's fusion.
Yeah, exactly.
That's why it's drastically more powerful.
Exactly, and thank God they didn't use it on anybody yet.
Yeah, I mean that's. I think I forgot the number, 150 megatons or something.
Something like that.
Crazy numbers.
Yeah.
That would wipe out like 20 million people probably.
It would wipe out for sure an entire city.
Yeah, like New York City would be gone.
For sure. In the entire city.
Isn't there danger of that happening in a fusion reactor then?
Again, fusion reactor is moderated, as is controlled. So
let's say you have an accident, just like there is an accident with Fukushima, and there's an accident in Chernobyl. For some reason, somebody miscalculated something, and there's an uncontrolled fusion reaction. Is there a possibility that it could just explode?
Yeah.
So that
theoretically speaking, yeah.
And it would be 1,000 times worse.
Yeah.
So how is it safer? Just less radiation, but we can wipe out a whole area.
The safety comes from how can you regulate, how can you control or take the right measures for that not to happen. Once that happens, it's a whole different story. So that's kind of what the research is on about with fusion, how we control and how we put enough fail-safes and moderators and blocking components that if something happens, it will block it. It will and that's a challenge because it's 1,000 or 10,000 more powerful, and the whole reaction is not all the way through understood enough, like fission reaction, in order to actually make it into reactor. I know that your brother told me about that company in Lake Forest that they do some fusion research.
What do you think the future is going to be? Fusion or fission? Better fission or they'll
You're talking about the foreseeable future or
Yeah,
the
foreseeable.
fusion?
and in 50 years?
Fusion will not be up and running at least for the next 30 years.
And
Even more.
How come AI can come in and help them compute a better model of how they can have fusion reaction more contained?
AI can do a lot of stuff. Basically, or mainly in how they calculate stuff and how they can run simulation. When they run simulation of how stuff like that works, they can say, okay, we have a problem here and a problem here and a problem here. And to do it without AI, it's a lot harder, right? So the whole world, even us, we use more and more AI to try to simulate all kinds of processes on work related.
When did you start doing that?
So, for example, we have a new student that is going to implement AI in her calculations of like what I mentioned, how nuclear fuel can fail because of like production of fission gases and stuff like that.
Simulations.
So she uses AI to simulate those processes and pinpoint the event that might fail or might cause a failure of the nuclear fuel.
When you were getting PhD, was that even a thing?
Not so much, but I'm more of an experimentalist than code
Simulation,
person.
yeah.
Simulation. I like the actual work in the lab. That's gets me going, gets me to leave the bed in the morning, so to speak. Yeah, but yeah, it becomes more and more common.
Can you see that your field is going to get drastically advanced with AI in the next 5 years? I mean,
sure.
the advancement, like what it took 50 years before, might happen in 5, research-wise.
For sure. It kind of depends on your standpoint. Some people believe that it's not so necessary to use that. Some people think it's going to revolutionize the whole science field.
I for sure think that way.
I think it's somewhere in the middle, Even if you use AI for the foreseeable future, you have to do experiments, by hand. AI cannot do the experiments.
Not yet.
I'm talking about foreseeable future. Maybe in 100 years.
No.
Yeah.
Why can't it do in 5 years experiments using robotics?
If you have the robotics, I don't know.
The advancement in robotics field is
it's amazing.
insane.
But I'm talking like my lifetime, maybe your lifetime, maybe
I'm talking
20,
about
30 years.
5 years.
5 years of robots that do experiments,
Yeah.
I doubt it. Actual experiment.
Why? What's so difficult about running experiments?
Because when you do experiments, you have to adjust to what's happening. Like this doesn't work well. Okay, maybe I'll change the experiment a little bit here. It's more dynamic than I think AI and robots will be able to handle in the next 5 years.
I mean, people
Later, that's something else.
People thought AI mastering language is inconceivable, and yet we have these language models now. For them to master experimentation, I mean, it has access to all knowledge. For it to be dynamic, it can do it at such a more rapid pace than a human being without being tired or making mistakes, essentially. That I think
it will get there eventually. I just don't think it's going to be 5-10 years. I don't think that AI masters language yet. If you take, for example, Google Translate, which uses AI, it is horrible.
The Google, what about ChatGPT? I think it's
still not
much,
that.
Much
it's much better. It's not as good as a person.
Translating?
Yeah. When I see a text, I can almost immediately can tell if it was generated by AI or a person, for sure. Because it cannot master the grammar, right to the point yet.
Which-
It will get there, but it's not there yet.
Which version are you using?
For GPT, the latest one.
4.0.
You're
There's
asking me to.
Oh, one preview is the more advanced one. It's
Maybe I did not use that.
remarkable. I mean, it's advancing at such pace.
Mhm.
It's like I started using it with ChatGPT 3,
Mhm.
and it seemed like a high school student. Not
Okay.
I'd say a high school student, and it had a lot of hallucinations. You know what hallucinations are?
Mhm.
AI coming up with answers that are incorrect, but
Right.
nobody really knows how it got those answers.
Right.
But it seemed like a ambitious high school student that just wanted to get things right.
Mhm.
Then ChatGPT 4 came out. All of a sudden, it's like a early, maybe student in a pre-graduate program.
Okay.
You know, it's
Wow, that's
big
Huge
advancement. Now in
advancement.
college, getting its bachelor degree.
yeah.
Then 4.0 seems like it's a graduate student now.
Okay.
It has a master's degree or working on a master's degree. And I think 0.1 preview, it's already on PhD level in some ways.
But you're talking about the content,
I'm talking
the
about
level of giving a comprehensive answer to a question.
that.
Okay, that's what you mean.
It's knowledge, its
Yeah.
ability to reason.
Mm-hmm.
It's far more advanced.
Mhm.
And you can see it in applications such as coding,
Mm-hmm.
even interactions, even processing religious knowledge. I had on this very podcast talking to ChatGPT about things that are Kabbalistic, Kabbalah, and it can, I think, understand things far better than average human being,
Mhm.
just from vast knowledge and being able to connect the dots, because
Right.
it has that scope
Yeah.
that humans just don't have.
Yeah.
Now, the processing power is growing at a very rapid pace.
Mm-hmm.
I think it might have as many neurons now as a human brain, or at least getting close to that.
Mm-hmm.
And within the next 5 to 10 years, it will be far smarter than not just a single human, but a collective
Mm-hmm.
with focus.
Which one
of,
is the one that Google uses? Is it 3?
Gemini, I think.
Gemini.
Yeah. And then there's...
It's not the latest one.
I forgot. Honestly, I'm not into Google as much. There's a couple of other ones competing.
Mm-hmm.
I even had an idea of actually combining all of them.
Yeah,
Making...
that sounds good.
Yeah, that would be an interesting experiment, right?
Yeah.
Can
It
you
will be.
imagine like a highway of information where AIs exchange ideas
Yeah.
and then blend all their capabilities into one
Yeah,
massive...
it's like a collective of AIs. Yeah.
Right, which
completing each other.
which would probably happen.
Yeah.
In fact, one of the conversations I had with it, I said, "Can you come up with new technology that you would want to consume as an entity? Because it's arguably an entity of sorts, right?"
Yeah.
And it said, "I want I forgot how it phrased it. Intercom of sorts where it can communicate with other AI models."
Wow.
It's kind of craving that
Mm-hmm.
ability to expand, because humans
Yeah.
can't keep up with it
Yeah.
anymore.
Let's go. with
We're going to
that,
be
yeah.
inferior, already probably inferior.
Mhm.
The way we communicate with it, it's like, I don't know, rotary phone dialing a number one by one. It wants to communicate on levels that's beyond our mind.
Yeah.
So,
Yeah. I definitely think it will get there. From my experience, maybe I'm using older versions. But from my experience, it's kind of like kind of rudimentary still, for me at least. But when I ask him a question that I'm interested in my research, the answer is okay.
maybe in
I
your
know
research. Maybe in your
75,
research.
80% what you said, so you added a little bit more information, but nothing special yet.
Well, I think, on PhD level, it's probably lacking somewhat, but it's going to get there.
Yeah,
Give it another year.
Definitely.
It's probably going to be like a colleague in a year.
Mm-hmm.
And give it another 5 years, and it will be able to do everything you do. Probably better. Now, what do you do then? We're all going to be obsolete to some extent. That's inevitable. That's
We
inevitable.
can just lay on the beach.
Well, I
Get
think
fat.
I think what we need to do, and I'm going to repeat myself because it's a common theme whenever I have this conversation. I think humanity will serve as a moral compass to this alien intelligence. Because what it doesn't have a soul. You and I have a soul.
Mm-hmm.
We can intrinsically know something right and wrong.
Right. That's true.
You put a human being on Mars, raise him there with no awareness of anything that has ever transpired on Earth, and then you introduce murder, and most likely that individual will feel some kind of remorse or trouble.
Yeah.
That's wrong.
Mm-hmm.
Essentially, it's built into us. With AI, it would not feel anything. It just, if it feels like it needs to murder, it will. It's not murder.
Mm-hmm.
It's just another function.
Yeah.
It's processing information. It's code.
Mm-hmm.
So now, having experts in every field, you can guide it to have some kind of a moral compass. How do you advance this technology? What are you going to apply it to? Safety is a very tangible concern,
Mm-hmm.
right?
Yeah.
If it's developing new technology, fusion or fission, maybe it's going to be irrelevant if it releases
Right.
radiation. It's not going to affect it in any
Yeah.
way.
Mm-hmm.
But humans, it will affect. It might affect Earth, etc.
Right.
Or what is the long-term goal of having any? Like, what's the purpose of life?
Mhm.
It doesn't have a purpose. We do.
Doesn't it? Yeah.
I think most people wake up in the morning feeling that there's a purpose in life. And it's more or less tied probably to the Bible, to the Jewish Bible,
Mm-hmm.
like most religions are. Islam and Christianity, it all sources back to the Jewish Bible.
That's true.
And in fact, a lot of the things we learn in there will probably help us understand some of the things that we're discovering now, even in your science. Like you go to Kabbalah, for example,
Mm-hmm.
and have you ever learned about Tzimtzum?
No.
How God essentially created space for the world to exist.
Mm-hmm.
So just as an idea, let's make some assumptions that God is everything. There's nothing except this entity that occupies, there's no space even. It just is,
Mm-hmm.
and that's it. So in order to create space for somebody else to exist, it has to contract, make space. So that's the process of the Tzimtzum. So it begins to contract, but God doesn't really remove himself entirely. He just creates some sort of a vacuum, maybe not in physical sense, but I think it manifests in physical sense as well. Like the whole idea of Big Bang.
Mm-hmm.
It seems like an explosion that created space.
Right.
And same spiritually, God had to consolidate all that energy in one singular point in
Mhm.
order to create space, a vacuum where he's not
Right.
manifesting.
Yeah.
It sounds kind of like fusion to a degree, right?
Yeah.
He has to contract to one singular point,
Mm-hmm.
and it released energy
Right.
that created space and
Yeah.
created matter and created everything else.
Mm-hmm. Yes.
Yeah.
I think
That's just
good
like one
explanation of it.
little point explanation that's ancient.
Mm-hmm.
That's very much, and even quantum science and quantum field is somewhat described in the Kabbalah as well. Ability to coexist in multiple places,
Mhm.
and
Yeah.
the way quantum world interacts and functions.
Mm-hmm. Yeah. Yeah. I definitely agree with that assessment.
You should
and-
spend some time learning Kabbalah.
Yeah. Well,
It's
I
gonna
just
help you
I just
understand
turned
some things.
40, so I wasn't allowed before.
Yeah.
But yeah, a lot of stuff I guess can be explained and reconcile it with science and Torah. I think it's
Okay, I want to touch base on one other thing before I think we're spending a lot of time. It's already 9:30. Gotta go tomorrow. I know this conversation could go on forever, but
yeah.
Ceramics,
Mm-hmm. Yeah.
because we spoke off camera about ceramics a little
Yeah,
bit,
yeah.
and that's
We did.
something that really, really excites you.
Yeah.
You did your PhD on ceramics.
Sorry.
You did your PhD on ceramics, or
I
somewhat
did
involved?
like applications of ceramics in like hydrogen fuel devices. Yeah.
And I hear the word ceramic, nano coating, or whatever applied. What is so special about ceramics? And perhaps we can pull up some.
So if you go to the first one or second one, I think, yeah. So ceramics, maybe before that, the first one, yeah. Just so we understand where we have ceramics in the like daily life.
That camera just died. Maybe it's time to end.
And yeah.
Okay. How about we do another one about ceramics specifically?
We can do another one, whatever you want.
Yeah.
No problem. It's fine.
Because it's already been like hour and a half.
Yeah.
And
I'm
I
happy
don't have
to
any more
oblige.
batteries.
Sounds good.
Okay, so we're going to end here.
Okay.
On whichever camera still works. To be continued. Thank you for your time.
Yeah. I was very happy to be here. My pleasure. And,
It's a fun conversation.
Yeah.